You know, in science, a lot of the time we're focused on building brand new things. But sometimes the most critical work is just making sure the things we've already built are solid. So in this explainer, I want to walk you through paper 37 from my research series. This is a paper where we basically take this really powerful mathematical engine we built, and we try our best to break it. We're going to push it to its absolute limits, just to see how tough it really is. So, here's the plan. We'll start with the big picture, just to get our bearings on where this paper fits in. Then, we'll quickly touch on the tools we're using before jumping right into the stress test itself. After that, we'll look at the results, talk about what they actually mean for the theory, and then wrap it all up with a look ahead. Let's dive in. All right, so to really get what paper 37 is all about, we gotta zoom out a bit. It's not a standalone thing, it's actually one piece of a much larger puzzle that my collaborators and I have been putting together for some time now. You know, the thing that drives this whole series of papers is one big, fundamental question. When we look at these incredibly complicated orbits that dynamical systems create, are there underlying laws? Is there some kind of order governing their statistical behavior? That's the challenge we're trying to tackle. And this timeline kind of shows how we've been building up our answer. It all kicked off back in paper 28, where we laid down some of the basic orbit laws. Then, in papers 32 and 33, we hit on something huge, a key structure we call the Watson band. Paper 34 brought in the real powerhouse, a tool called the twisted Lasota-Yorke inequality, which gave us our first taste of rigidity. Paper 35 made that rigidity unconditional, which was a big step up. And finally, paper 36 showed that this entire structure was universal, that it worked for several different systems. Each paper was really a crucial building block. So where did all that work leave us? Well, it led to this really powerful conclusion. We proved that this key property, this rigidity, exists. But, and this is a big but, only inside a very, very narrow window for our main parameter, epsilon, between 0.84 and 0.90. Now, that was a fantastic result, but it left us with a pretty obvious question. And that right there is the entire motivation for paper 37. Exactly how robust is this thing we've built? If we start pushing epsilon lower, or maybe crank it higher, does the whole theory just fall apart? Or does it actually hold strong? We wanted to know if we could confidently say our spectral picture is valid over a much wider range. So, just to be super clear, the goal in this paper was not to invent a new theorem. The point was to take the powerful one we already had and really put it through the ringer on a much bigger grid of parameters. This is all about validation, about quality control for the theory. So, to run this stress test, I'm bringing in the big guns, the theoretical machinery we built in those previous papers. Now, we don't need to get lost in the weeds of how these tools are constructed. For our purposes today, we can just treat them as black boxes and focus on what they do. Okay, first up is the twisted Lasota-Yorke inequality. This thing is the absolute engine of the whole framework. The best way to think about it is as a guarantee that keeps things from getting too wild. It tells us that the total variation, you can think of it as the complexity, of our system doesn't just explode into chaos. It's the tool that tames the system, and it makes everything else possible. And because we can control that variation, we get this incredible property, an abstract BV spectral gap. This is the result we're really after. It basically means our system has one main, dominant, stable state, and that any other weird behaviors just fade away really, really quickly. In a nutshell, it's what gives us predictability. And the last piece of the puzzle is what I like to call the KL bridge, which comes from Keller-Liverani perturbation theory. Think of this as our sensitivity meter. The spectral gap tells us the system is stable at one specific value of epsilon. The KL bridge tells us what happens when we tweak that epsilon. Does the whole system get shaken up, or does it stay put? This is what we need to prove rigidity across a whole range of parameters. Okay, so we've got the toolkit. How did I actually go about doing the stress test? Well, I used a computational method called a certified Ulam scheme, and I unleashed it on a much, much wider grid of parameters than before. Instead of that tiny little window we had before, check this out. We're now testing a set of 9 different epsilon values, going all the way from 0.70 up to 1.10. And just to be extra sure, at every single one of those points, we ran the test for 3 totally different system types, what we call kernels. The process itself is pretty straightforward, really. First, we chop up our system's interval into 1,024 little cells. Then, we use a bunch of Monte Carlo samples to build a big matrix that approximates what's really going on. From that matrix, we can calculate a raw spectral gap. But here's the crucial part. We then apply a really rigorous error model from the previous papers to get a certified conservative number. This isn't just an estimate, it's a lower bound we can actually trust. And here's the key takeaway on this. This Ulam scheme acts as our diagnostic tool. Because of all that powerful theory humming in the background, we have a mathematical guarantee that the number we get from our computer is a really good approximation of the true, deep mathematical spectral gap. So if our certified gap is positive, we have very strong evidence that the real one is too. So this brings us to the moment of truth. We ran the test, we pushed the parameters, we crunched all the numbers. So what happened? Did the theoretical framework actually hold up under all that pressure? And remember, this wasn't just a single calculation. This was a whole campaign. We ran 27 separate, high-precision simulations to cover every single combination of our 3 kernels and 9 parameter values. A ton of computational work went into this. And the result? Well, it was a resounding success. Honestly, even better than I might have hoped. In every single one of those 27 tests, without exception, the certified spectral gap was strictly positive. The framework didn't just survive, it proved to be incredibly robust. Let's actually look at the data. Here's just a little sample of the certified gaps. You can see they're all clearly positive, but just look at the numbers for that Lorentzian kernel. At an epsilon of 1.10, the gap is almost 1200. That is just screaming stability. It points to an incredible level of predictability in that particular system. But here's the thing. The most important number on this screen isn't the biggest one, it's the smallest one. Across all 27 tests, the absolute worst-case scenario, the minimum certified gap we found was 0.6509. Now, having this single positive lower bound, this gamma min, that holds uniformly across everything, well, that's the absolute key. It's the linchpin that lets us extend the whole theory. So we have this great number from the computer. Awesome. But how do we turn that back into a stronger, more powerful mathematical theorem? Let's connect the dots. And this slide right here shows the payoff. We started with this proven rigidity window that was, pretty narrow. But thanks to the stress test, we can now draw a new, much larger box. We call it iRig, that we know contains both our original window and our entire widened test grid. So here's how the logic flows step by step. First, our stress test confirmed a positive spectral gap across the whole wide grid. Second, because that gap exists everywhere, our sensitivity meter, that KL bridge, still works perfectly. It doesn't break down. Therefore, we can conclude that the core structure we care about, the Watson band, stays rigid across this entire much larger interval. We successfully extended the theorem's reach, big time. Okay, let's zoom out for one last checkpoint. What's the main takeaway from all this, and where could this lead us in the future? If there's one thing to remember, it's this. Paper 37 is a robustness checkpoint. It's all about taking an existing, powerful framework and showing that it's resilient, that it's reliable over a much wider range of conditions than we originally proved. It's about building confidence in the tools we have. And that leads to a pretty exciting thought to end on. Now that we know this framework is so tough, could we use this exact same stress testing approach to validate completely new systems we haven't even thought of yet? Or maybe even, could this kind of analysis one day be used to guarantee the stable behavior of autonomous agents in really complex environments? That's the thought I'll leave you with. Thanks for watching.